Okay, I think we're recording now. Here we go. All right. Radio waves, we know about that. And here's the experiment that they did that Morley and Michelson, well, Michelson did. He got the Nobel Prize for it, for actually coming up with the speed of light to that level of accuracy. And they finally figured out that it traveled in a vacuum. Yeah, I wish we had time to do the relativity portion. I wish we had time to do several other things too, but we just didn't. Rotating octagonal mirror based on the out and back thing, but they needed to have it be far enough away so that their detectors could pick it up and be able to rotate this huge octagonal mirror. I mean, it was huge. And it hit a fixed mirror on a nearby hillside. Just amazing. Just an amazing little experiment. Oh, I'm going the wrong way. All right, so anyway, Maxwell's prediction of the speed of light. Look at that. I think I had you do that in class. Did we do that in class? If you do this, where you take the permittivity of free space times the permeability of free space, take the square root of it, then take the inverse of that, you'll wind up with what the speed of light is. This was what fell out of Maxwell's equations. This is why the speed of light is the cosmic speed bump. It's not because we just decree that the speed of light is the speed of light. Nothing can go faster than that. It's just that the laws of nature say that nothing can go faster than that based on what we know so far. There's absolutely no, that's just the way it works. And this is interesting. We don't have any problems, I don't think, with the energy in microwaves, but electromagnetic waves, like water waves, carry energy, okay? And so the electromagnetic, the microwaves, which is what they are, come shooting out, go hit the bread that you're warming up here, which is composed of a lot of water. Well, water is polarized molecules. This energy hits them. They get agitated. They speed up. They collide. What happens when molecules smash into each other? They heat up. Boom. And it happens very quickly because you're at the molecular level getting these things to heat up. Now, some things don't. That's why there's certain, like plastic, doesn't heat up very well. Eventually it will. We're not doing this. We are doing this. Okay, so here we go. And this is where this gets kind of tricky. So I'm going to go to my unpolarized light. But first, I want to show you physically what's going on. Oh, so I didn't want to do that. Let's go back to this. So, all right, rope vibrations coming in. Easy to pass through that slit, okay? But it can't pass through here. It doesn't turn into a wave anymore, all right? Same thing, here we go. Single direction of an electric field. This is the polarized light, okay? Random electric field directions, all right? So anyway, unpolarized light. So the electric field is coming in all over the place, all right? And when it hits a polarizing material, it loses half. What it does is, if we go back here, I wish I knew how to go. If we go back to this thing, look what's going to happen. All the ones that are coming out to the sides are going to get cut off. And remember, these are vectors. Electric field is a vector, so we can break it down to its components. So it loses all of its X components, each one of these things. So the only thing that gets through is the Y components. So in other words, so it's lost half of its intensity. And by the way, intensity is in meters, is in watts per meter squared. So let's write some of this down, right? Just some ideas that you need to know. All right. First of all, intensity. Intensity is measured in watts per meter squared. In other words, the intensity of something, the further out, I mean, the equation of it makes sense. The further away you get away from something, you know, so if I'm going to send out, if this little beacon here is going to be sending out spherically, and I'm talking spherically here, you know, if this is a sphere and it's going out in all directions, all right, then we're talking about the surface area of a sphere, which is 4 pi r squared, okay? Surface area of a sphere. And so the sun hitting the earth, hits the earth, this is just a fun fact to know, hits the earth with an intensity of 1,300 watts per meter squared, which, you know, that can heat something up. However, if you take a magnifying glass and take that 1,300 watts per meter squared and focus all that light into something that's, you know, millimeters squared, that's pretty intense. That's a lot of energy. That'll burn through a leaf. That'll burn through, you know, a hole in your jeans. That'll kill a lot of grasshoppers if you can get them to hold still. No, kidding. All right. So that's the intent. So that's the intensity coming in. So polarization knocks out half the intensity. Okay, polarization knocks out half the intensity. All right, so just wanted to make sure we were square on all that. Let's go back to our slideshow. So yeah, I'm going to stop doing that. So this is what the polarizing material knocks out half of it. And this is Malou's law. This is Malou's law. In other words, you get the intensity after the analyzer, S. This is the intensity after the analyzer, after it goes through here. So it's this polarizing thing. Then we have another polarizing thing. We kind of tilt a little bit here. Just kind of tilt that a little bit here. And the intensity that's going to come out and hit our photocell is going to be the half of the initial intensity that came in at S naught over here times cosine squared of this angle. Off, again, is the angle off the normal. In optics, we take all of the angles off the normal, okay? So what value theta should be used so the average intensity of the polarized light is 1/10 the average intensity of the polarized light? Let me show you what they're talking about here, okay? And then I'll show you physically why this works, and it's really kind of cool, and we're going to stop here. And then I'll start the problem here.